Okay, so welcome to the XPS workshop. My name is Nargis, and I'm the Create Correct Program Coordinator at Western University in London, Ontario, in Canada. And today we're going to have the XPS workshop presented by Dr. Mark Biesinger.
Hello, everyone. My name is Yolanda Hedberg. I'm the director of the CORRECT program that is organizing this. I also have worked with Mark Biesinger for at least 5 years now. He has his master from our department, which is Department of Chemistry at Western University, and he has been at Surface Science Western for almost, very long time.
30 plus.
30 plus years. His PhD is from University of South Australia, and he has worked with XPS almost the same time as he has been at Surface Science Western. So a long time of practitioner experience. And he's also a very collaborative person that is committed to training others. And you might know he has the XPS fitting webpage that most of you probably have looked at. So we got a lot of questions, so he will answer them in themes in the second part of this lecture. And anything that's not answered, you can either try to contact him afterwards, but we will also make this recording available and other resources to everyone who was registered. So please join me in enjoying Mark Biesinger's workshop, and I will be quiet now. Thank you.
Okay. Welcome. We've got a pretty good turnout by the sounds of it, which is really nice to see. We're going to go through a little bit about X-ray photoelectron spectroscopy, a little bit of the basics, some more advanced curve fitting, and some advanced studies, and then we'll get into answering some of the questions that you have. So I'm located here at the Western University in London, Ontario. We have we're located about halfway between Detroit and Toronto. For those of you on campus, we're at the Convergence Center up on in the Western Research Park. The lab I'm director of is called Surface Science Western. We're Canada's leading surface analysis materials characterization facility. We were established in 1981. We can have 16 full-time staff members, probably somewhere over 300 plus people years of experience in surface analysis, over 300 plus publications by staff. Our user base, we're run as a institutional core research facility and a self-sustaining ancillary business unit. Our user base includes Western graduate students and faculty, university groups from around the world, as well as we work with around 150 to 200 different companies from across North America annually, issuing somewhere around 1,000 technical reports per year. We're a fully equipped lab. We've got 3 scanning electron microscopes, a couple of XPSs, dynamic sims, TOF sims, as well as a whole range of other equipment. So let's get into XPS spectroscopy. Myself, as well as a large group of XPS practitioners from around the world, have been working over the last quite a few years, looking to try to improve methodologies and understanding of XPS. And you can see these are just some of the publications that have been put out. There's been a large amount of effort looking at what we're seeing is a lot of errors in XPS interpretation within the literature, and so there's been a big push by people to try to improve that. There was one study that was done looking at a very small subset of XPS data from 3 different journals over 3 or so years. And again, here's some more of those papers that are looking at to help their guides and things like that people can use for this. So X-ray photoelectron spectroscopy. XPS is good at looking at elemental and chemical state analysis of the outer surface of solid samples. Effective probing depth of somewhere around 5 to 10 nanometers, which will vary depending on the composition of the sample and can also be varied with the electron takeoff angle or the sample angle. You can detect elements from lithium through to uranium. It's quantitative. Detection limits range from as low as 0.01 atomic percent, and in some cases, but in some cases, much less than that. And you can tell things from get chemical state information. So whether you have an oxide versus a hydroxide versus a carbide, silicone versus silica, nitrides versus um, elemental silicon, fluorocarbon versus fluoride, etc. This is what we have a number of XPSs. The one in the front was a Kratos Ultra that's been decommissioned. In the back, we have a Kratos Axis Nova. And currently, we have the Kratos Axis Supra system here at Surface Science Western. XPS works on the photoelectric effect. Basically, shine X-rays at the surface. Photoelectrons are ejected. To get X-rays, you use an electron gun, hit the surface of an anode, such as aluminum or magnesium, run that through a crystal monochromator down to your sample surface. Photoelectrons are produced, and you measure the kinetic energies of those photoelectrons. And those kinetic energies can be used to calculate the binding energy of those elements or those core electrons from the various atoms. So again, usually what we are using in this case, aluminum K alpha X-rays at 1486.7 EV. Shine at this is a nickel sample, kicks out a photoelectron. The kinetic energy is 634.2 for a 2p3 has photoelectron. You can then calculate that back to be 852.5 EV binding energy. Spectroscopic nomenclature follows these rules. So you have your principal quantum number of 2, orbital angular momentum, total angular momentum to define what orbital the photoelectron comes from. Some of the X-rays that are commonly used for XPS, the most common is aluminum K alpha X-rays. Probably the next most common, but you don't see it much anymore, is the magnesium source. We're seeing a lot of work now using higher energy X-rays to go deeper into the sample. For example, our Kratos Supra also has a silver L alpha source at 2,984 EV. Yeah, and again, those are the standard X-rays. You can also have helium-1 or helium-2 ultraviolet light, which is used for ultraviolet photoelectron spectroscopy. Or you can also use a synchrotron, which has a high-intensity tunable source. And you can tune that to get your optimal surface density, generally using a photon-electron energy of approximately 40 to 50 EV above the peak of interest. And the way that works is if we look at what's called the inelastic mean free path. So this is the path. It's the 1 sigma or 68% of photoelectrons can escape from the surface without energy loss. So if you have 3 sigma, that captures about 99.7% of all photoelectrons that come from that depth. And if you talk about, you have like a tunable source, you're trying to get your synchrotron tuned to be about 40 to 50 EV above this kind of curve here. And so that will be your maximum surface density available by XPS. Another way that you can change the depth of analysis is by changing the takeoff angle of your sample or your tilt of your sample. So if you have a normal takeoff angle, that's your maximum depth. So this is your spectrometer would be up here. Photoelectrons are coming straight out here. If you tilt your sample, you're now changing that 3 lambda to a shallower depth as you tilt that sample. At about 30 degrees takeoff angle, you get about 50% of the depth about 90 degrees. At 15 degrees takeoff angle, you get about 25% of the depth at 90 degrees. General analysis usually starts with what we call a survey scan. This is where you scan the binding energies from 0 on up to, say, 1100 or 1200 EV. And you get peaks that look like this that can then be assigned to the various elements that are present. So if you have something at 285, you have carbon, you've got an oxygen peak here. Sometimes you'll see other peaks as well. So for example, we have a fluorine peak. We see the 1s orbital, but we also see structure from the fluorine Auger signal as well in here. Something like silicon, we've got two peaks that show up, silicon 2p, silicon 2s. And you can use what they call relative sensitivity factors in conjunction with areas under these curves to figure out how much of each element that you have present. And that's usually a very good start, and you get a lot of information just from doing that very quick analysis, understanding what elements are present at the surface and how much of each of those different elements are present at the surface. I recommend that whenever you do XPS, you're always including a survey scan in your analysis, not just high resolution work. If you have an unknown sample, you want to go through and look at the various peaks that are present, look at the binding energy of those peaks, and those kind of you figure out what these are, and there's tables and things like that that you can go through and pull out what elements should be there. A lot of the times, if you have, say, a silicon 2p peak, you have to also have a silicon 2s peak. So if you only have that one peak, then it's not silicon. It's got to have both peaks present for that to happen. Same with something like chlorine. You've got a peak at 200, a peak at 268. If you only have a peak at 200 and no peak at 268, there's probably a chance that it's not chlorine, it's some other element or some other interference. Chemical state determination. In theory, small shifts in the core level binding energies are indicative of metals or chemical state changes. So whether you have the metal or oxide, silica versus the silicone, fluoride versus fluorocarbon, etc. As you withdraw valence electron charge, you decrease shielding and increase the binding energy that you get. As you add valence electron charge, increase shielding, you see a decrease in binding energy of those core electrons. For most elements with uncomplicated peak shapes, a simple binding energy reference is usually sufficient to figure out what you have. And there are databases, although unfortunately the NIST database is down now, things like the Phi handbook, my website that has a whole collection of reference energies. Literature values can be good, they can be incomplete, they're just not done, or they can be wrong. So you do have to have watch what you're looking at and watch what you're referencing. As I mentioned, some of the literature out there has not been well vetted. And so there's mistakes in there, and we're seeing some problems in the literature. So you got to be very careful. Some of the things that you should check for when you do look at literature, things like is there details about calibration of the instrument? What sort of charge referencing has been used? And we'll talk about charge referencing a lot later on. Looking for things like data consistency. We're seeing a lot of people fitting peaks to noise, widely varying full width half max, no constraints on their curve fitting, those sorts of things. Do they show all the data, or is it just cherry pick data? We have the ability to put in lots of spectra into supplementary data, and so there's no excuse not to show most of your data or a lot of your data anymore. One of the big things we also see, indications of sample charging issues or differential charging as well. So if we go into looking at the survey scan and we zoom in and use a much better spectral resolution, we get what's called a high resolution scan. So this is a high resolution scan of the carbon 1s signal. And you can see that in the survey scan, we see, peak with a little bit of structure, but when we zoom in, we've got this kind of multiple structured peak here that can then be curve fit to show, well, we have so much carbon bound to carbon. We have up here carbon triply bound to fluorine, carbon bound to two fluorines, and a whole bunch of species in between. And the area under the curves can tell us how much of each of those species are present. So it's a pretty simple one-to-one ratio on these simple sort of peaks. For high resolution spectra, again, an S orbital spectra, the binding energy shifts gets most of the information. It's a nice single peak. For P, D, and F orbitals, things can get much more complicated. So before we get into those sorts of things, I want to kind of go through some analysis of just some spectra using what our curve fitting software. We use a software called CASA XPS here at Surface Science Western, but there are other packages available. There's a new one out called Curve Fitting from a group out of England that's quite good. There's things like Unifit. There's the multi-pack software on the Phi systems. There's Advantage out of Thermal, and they all do similar sort of things. So I just wanted to kind of go through what we do when we want to look at, I've got to move this strip here for a sec. What we want to do, say, when we want to do a survey spectrum, for example. So we have this survey spectrum, and we want to kind of go through and figure out, well, what peaks are present. And so we have a library that we can pull up. And if you can pick on the peaks and go, okay, well, that's a peak here, and that looks like it's probably oxygen. You can zoom in, look at the peaks and go, okay, well, what's this peak? 281, okay, that's probably carbon. And there's some, background knowledge. And as you start doing this, you get pretty fast at figuring out what elements or whatever. You can also go into a periodic table. If you know a little bit about your sample, you can say, okay, I know I've got carbon, I know I've got oxygen. I believe I have some sodium. Yep, I've got that. Probably some other salts, some calcium. I know that there's a peak here at 400 that's nitrogen. And then down here, if I zoom in and take a look, I've got some more peaks here. That looks like it's a sodium peak. What are these guys? So we've got these two peaks here, and we kind of know that that's a silicon. And so once we've got our elements identified, we can then say, okay, well, let's put some labels on here. And so, okay, there's oxygen. We've got an oxygen Auger, carbon, sodium. We can pick all the peaks that we see are present. And again, this is this is information. If you're using CAS XPS, we have some good information on my website that you can follow along and go through and do this kind of thing step by step. So we'll apply some peaks. Okay, that's great. We can get rid of our, take a look if we've got everything. It looks like we've got most of the peaks present. We go into what we call a quantification menu. And here we can just go, okay, we're going to create from labels. So we create a background in all these different peaks. Now, obviously, we've got more peaks than we should have because we've got two peaks for quantifying for oxygen. We only want one, so we're going to use the main peak, the main 1s peak, and the rest we're going to delete. I'm going to delete the sodium alpha or Auger peak, the 2s, the 2p, the calcium 2s. We're going to remove the calcium 3s, silicon 2s, and then we've got what peaks are remaining that should be used for quantification. And if we go to our annotation, and if we can just say, okay, I want to put some regions up to see how much I have of each of these things, hit apply. There we've got quantification of all this stuff, but some of this isn't right yet. So we've got to go and take a look at where our backgrounds is. So if we zoom in, we want to make sure our background's across this. And here I'm using a Shirley background. We want to make sure we get our endpoints look good. So it looks good there for that sodium peak. We just move on down the way to see what else we have. You can see here this oxygen peak, we're probably not getting right at the baseline. So we're going to move that a little bit to get it nice that it goes across the peak quite nicely. Nitrogen looks not too bad. Oh, calcium's not where it should be. So we're going to move this whole window to make sure that we're across the calcium peak nicely. Now you can see that we're quantifying calcium properly. The carbon looks good. If we go down the silicon, we've got some problems here. So we're going to move that around to get it to that we have nice backgrounds across the area. And so that's just quickly going through and quantifying our survey scan. And again, that I know it's gone through very quickly, but there's more detailed instructions on my website if you want to do that in CAS XPS or with other softwares. So we've done that. The next thing we're going to look at is doing a simple curve fitting of the carbon 1s peak. So for insulating samples, we'll get in, again, I will talk about this a lot in the question period. We need to, as photoelectrons leave the surface of an insulating sample, that sample is going to build up a charge. And so if you don't compensate for that, your effective binding energy will start shifting. It'll start moving upwards until it finally disappears and you don't get any signal at all. And so to fix that, what we normally do for insulating samples, we'll hit that surface with a flood gun of electrons or sometimes charged ions to compensate for that charge, and it'll reach a steady state. And usually what happens when you reach that steady state, you've pushed it down, the apparent binding energy is down for all elements down a little bit. And so we need to do what's called charge correction. So if we look at something like carbon 1s, and the aliphatic peak for carbon is a common charge correction. And again, we'll talk about a lot about that later. But I want to go through and do a quick curve fitting of the carbon 1s peak to just kind of show you how we go through that process. So the first thing we do is we're going to create a background. And in this case, it's a Shirley background. There are other backgrounds possible, but a Shirley is a very commonly used background that for most cases is sufficient. And we're going to set our endpoints across that background so that we have a nice background across there. Then we'll go into components, and we're going to create a peak. And so we have a peak at that starting one. Obviously, that doesn't cover all the area under the curve, so we'll create another peak and maybe one more that for this peak over here. We can change that full width half max. And if we do a simple fit, already we've got a pretty good fit of that peak. You can go in and you can change the labels of that. So this we know is carbon bound to carbon, carbon bound to hydrogen. So that's our aliphatic backbone of whatever this material is. It's basically a piece of Scotch tape is what we're looking at. If we put our labels of our components on, you can see we have 3 peaks with varying widths. For something like this, where it's fairly well defined, you could probably get away with letting the full width half maxes be unconstrained. A lot of the times, though, for something like this peak, obviously we're going to fit that to be exactly that peak width. For these 2 peaks, what we may do is we may want to constrain those peaks to have the same full width half max. So this was likely our carbon singly bound to oxygen peak. And we can go in and we can change that the constraints of this peak are the same as peak 1 or peak A. You can see now they both have a full width half max the same. And if we refit, it seems to clean up the fitting a little bit. And it looks like we're getting a pretty good approximation of what's going on here on this sample. Now, because as I mentioned, this sample is insulating and we're using a charge neutralizer to correct that, this peak is not where it should be. This peak should be somewhere around 284.8, 284.5, something, or 285. But it's not. It's shifted downward to 280.7. And so we want to shift that peak up. But we also want to shift the peaks up for those elements that we also took at the same time. So the oxygen peak is going to be shifted down. The nitrogen peak is going to be shifted down. And so what we're going to do is we're going to select all these peaks, go down. We're going to go to processing. And that is not the right thing. Where is my processing? Sorry. And we're going to go calibration. And we're going to take the measured peak, so this aliphatic peak at 280.76. And we're going to charge correct to 284.8 EV. And we're going to shift everything. And we're going to apply this to our selection. And so now we'll shift this peak up. So now this is charge corrected. This oxygen peak is now charge corrected. This nitrogen peak is now charge corrected. So now we can go to those peaks and say, okay, well, what's going on with the nitrogen? What do we have present? The carbon, we have carbon bound to carbon, carbon singly bound to oxygen at 288.7. This is carbon probably as, so this sort of functionality down to 2 oxygens. So what's going on with our nitrogen? Again, we can apply a background, run that across our peak, fit in a component, see what its binding energy is, 399.4. So that tells us it's probably an amine or a amide type functionality within this material. So we've got that figured out. We go to the oxygen peak. Maybe we'll take a quick peek at the survey spectrum. The survey spectrum, we see we just have carbon, nitrogen, and oxygen. So there's no other contributions other than organic type oxygens present. And again, we can go in and we can do put a region down across the background, create a couple of peaks, see how they fit. It's not too bad. We've got some pretty good resolution. And we've got a couple of peaks with a certain amount of areas, and we can go in and look at the tables and say, okay, well, this is a certain type of organic oxygen. This is another type of organic oxygen. Obviously, we have two very distinct species here on this surface. So that's kind of just kind of a quick going through some very simple curve fitting of these sorts of things. It gets more complicated. All right, as we get into higher orbitals, so the 2Ps, the 3Ds, the 4Fs, and things like that, things can start getting a lot more complicated. And in particular, the transition metal species show a lot of further complications. So the metal 2P spectra from transition metals, you can get contributions from spin orbit splitting. You can get asymmetric peak shapes, plasma and loss structure. You can get shake-up structure and things called multiplet splitting. And generally, you have a lot of overlapping binding energies and peak shapes for many of the elements present. So spin orbit splitting. The S levels or S orbitals will give rise to a nice single peak. And so that's what we saw with the carbon 1s, the nitrogen 1s, and the oxygen 1s. So it's very single peaks tell you what different species are present. For the PD and F levels, you're going to get what we call a doublet, or from spin orbit splitting or J to J coupling. So the peak areas that you get should match with theory. If not, there may be other species present. So what I mean by that, for say a p orbital, you have J values of 3/2 to 2/2. The number of electrons are 4 to 2, and so we should have an area ratio of 2 to 1. And if we look at something like the scandium 2p peaks, we have an area ratio of 2 to 1 for the 3/2 to 1/2 peak. The d orbitals, you'll have an area ratio of 3 to 2, and for the f orbitals, it'll be a ratio of 4 to 3. And if it's not that, then something else is going on. For conductive species such as metals and graphite and those sorts of things, you can get interaction of the core electrons with the conduction band, and these will cause small losses of energy that show up as an asymmetric tail on the higher binding energy sides of the metallic peak. So for something like, say, a titanium metal sample that's been sputter cleaned and polished and all that sort of stuff, so it's very pure metal, this peak shape is no longer that nice Gaussian Lorentzian peak shape. It's now an asymmetric shape. And so you have to take that into account when you do your curve fitting. You have to fit this with an asymmetric peak shape. You don't put a Gaussian here and another Gaussian here and another Gaussian here and say, okay, I've got titanium metal, titanium 2, titanium 3, etc. You have just titanium 0 and this asymmetric shape. So you have to take those things into account when you're doing your curve fitting. For some metals, there's also the possibility of loss of a specific amount of energy due to interaction between the photoelectrons and other electrons. With metals, you get this energy loss to the conduction electrons arising from group oscillations, and this is called plasma and loss structure. It's can be very dramatic for some species. For example, for aluminum and silicon metal, we get these very strong plasmon lines showing up at consistent energies above the main photoelectron peak. Um, Generally, it's not too much of a problem for curve fitting of high resolution spectra, but in your survey spectra, a lot of times what we'll see is people will think, okay, well, this is another species. And we say, well, is this, is this peak here silicon? Is this peak silicon? Is this phosphorus, etc. When it's not, it's actually just these plasma loss structures that are showing up. Shake-up structures. Um, There can be a finite probability that the ion will be left in an excited state a few eV above the ground state. And when this happens, the kinetic energy of the emitted photoelectrons is then reduced. And this will be seen as peaks at higher binding energies above the main line. Oh, having some mouse issues. Hold on a sec. Okay, there we go. And so if we look at a spectrum of the copper 2p spectrum of copper hydroxide, this is the classic shake-up structure we see for copper 2 species. And we see that this structure above the peak here is what we're having. If we look at something like multiplet splitting, multiplet structures arise when an ion has unpaired electrons. So for example, chromium-3 is 3p6, 3d3. And so when you have a core electron vacancy being made by photoionization, you can then get coupling between the unpaired electron in the core with the unpaired electrons in the outer shell. And this will create a number of final states which will be seen in the photoelectron spectrum. So instead of a nice single peak here, you get all this structure showing up within the spectrum. And this was predicted many years ago, some of the work by Gupta and Sen, where they modeled what this kind of multiplet structure would look like for all the different transition metals. You can see that they're not nice sharp single peaks. All these things show up as multiplet peaks. And so this can get very confusing very quickly, particularly when you have even databases such as the NIST database saying, okay, you have a single binding energy for chromium-3 oxide, even though you've got a peak that has all this structure to it. So which peak does that refer to? Same thing for nickel. Nickel will have all this structure that shows up, and yet in the database it says, oh, it's a peak at 855.5 EV. So that doesn't really make sense. So that's caused a lot of confusion out in the literature where people are still looking at these structures and going, well, I have this peak here. Well, this is chromium-3. Well, this must be chromium-4. This is chromium-5. This is chromium-6. When really all you have is chromium-3. So we've seen those sorts of problems out in the literature where they're trying to identify this structure as actual chemistry when it's just one chemistry. If we look at across the transition metals, first row transition metals, and we look at all the species that can show this multiplet structure, the ones in red will have multiplet structure, strong multiplet structure very present. The stuff in green are either the metals or do not have unpaired electrons, and so they will not show any multiplet structure. The ones in yellow technically do show multiplet structure, but it's not well resolved, so sometimes it kind of just shows up as a broadened peak to be present. So when we have all these complications, how do we accurately identify the species that are present? And then how do we quantify those species that are present? Because we want to know how much of each of these things that we have. And so we've gone to a process where we do a standardized fitting procedures for the metal 2p spectra based on generally extensive analysis of quality standard samples. and then we look at those standard samples, and we curve fit based on the fact that there should be spin orbit splitting. If the splitting is not sufficient to separate out the 2p3 halves and 2p1 halves features for all the different species present, we take that into account. We'll take into account peak asymmetries for the metal structures or conducting materials. Look at things like shake-up structures, and then we'll model a lot of the multiplet splitting to see that total peak shape. And we'll use the total photoelectron yield for each species to determine the percentages present in unknown samples. So if you look at species without significant multiplet splitting, something like scandium, we're going to have an asymmetric peak shape for the metal. We're going to have a nice doublet for scandium 2 or scandium 3 oxide. This doublet is going to be have a 2-to-1 aerial ratio. We can get the full width half maxes from these standard spectra, and then we can go and basically apply all this with proper constraints. So we're going to constrain the peak positions between the 1/2 or the 3/2 and the 1/2 peak. We're going to constrain the positions of the metal and also a defined peak shape for the asymmetry. And then we can plug that into a model that then curves fit these unknown samples, and we can pull out, how much scandium metal we have, how much scandium oxide we have, how much oxyhydroxide we have at different binding energies. It's a relatively straightforward fitting with the proper constraints applied. Similarly, for something like titanium, we can do the same sorts of things when we have tables of all the different values for the splitting values for where the different species will be, the various different oxidation state species will be, how to fit that asymmetric peak shape. And again, we can go in and we can say, okay, we've got so much metal, so much titanium 2, titanium 3, and how much titanium 4 oxide that we have present. If we get into species with have a lot of multiplet splitting. So when we first got into this, one of the first ones we looked at was the chromium system. The literature was generally not great. There was a lot of confusion out there. And again, I talked about how the databases were quoting a single peak binding energy, but for compounds that were known to have multiplet split peaks. And a lot of people were, again, assigning this structure to a whole bunch of chemical states when really only chromium 3 was present. And so if we look at a bunch of standard samples, we have our chromium 3 oxide up here, where we're able to model using a series of peaks that basically just mimic this peak shape. And so we have 5 peaks here of assigned splitting. So the peak width or the distance between all these peaks are known. The areas of those peaks are known, and the full width half max of these peaks are known. And we're just using that as a model to model the shape of this structure. Something like chromium hydroxide over here has a broad single peak that we can model that shape with at a certain binding energy. Something like chromium 6 doesn't have any multiple splitting, so we have a nice sharp peak at a known binding energy that we can use. And we set up kind of these rules for how to do this curve fitting. So for chromium 6 species, we're going to have one narrow peak ranging from 579 to 580 EV that will model the chromium 6 species present. We'll model the chromium 3 species, one set of peaks for the chromium 3 oxide and a peak for chromium 3 hydroxide. Again, with all well constrained and within a specific binding energy range. And then again, the metal, we're going to have an asymmetric peak shape assigned to that. And then when we apply this to unknown systems, we can pull out how much of the different species we have present. And it can pull out very small changes and subtle changes for that matter. So we have here a decorative chrome plating where before surface cleaning treatment, we had so much metal underneath with mostly chromium hydroxide on the surface. And after surface cleaning, we still saw kind of a similar amount of oxide and hydroxide, but it was now more oxide present along with chromium hydroxide. So it's a more structured, less hydrated surface. If we look at something where we're trying to pull out how much chrome 6 is present, this is a chromated zinc-plated steel. And again, we're able to see, okay, we got a chromium 6 of about 15%. Because of the overlaps with all the different structure, our detection limits for chromium 6 somewhere between maybe 5 to 10%, depending on the samples that we're looking at, within a mix of chromium 3 species. Next up is nickel, and you can see that there's a lot of shape to these peaks. So these have both multiplet structures here, and then shake-up structures here. So we've got information coming from all these two different phenomenon. If we look at our metal, we have an asymmetric peak shape, but we also have some satellite structure that we have to model and put that into the model for area under the curve. But if we look at our two different, say, common nickel 2 species, nickel 2 oxide, nickel 2 hydroxide, you can see that the shapes of these peaks are very different, very, very different. And so even though they're both nickel 2, we're not going to look at these systems and just go, okay, I have nickel 2 or nickel metal. We're going to say, okay, I have nickel 2 oxide, or I have nickel 2 hydroxide, or I have nickel 2 sulfate, or whatever it is. But you can pull out individual species very well because of the shapes of these things. And so we model all these sorts of things. If we look at other systems, we've got nickel ferrite, nickel chromate, again, very different looking spectra. So it's the spectral shape as well as where its positioning is, gives you all this sorts of information. So again, if you think about what the NIST database is telling you, it's giving you a single peak for kind of this peak position, but that doesn't tell a story really at all. It's all the shapes of these things that are telling a story. And then we have over here, we have a nickel 3 species that will again have its own unique peak shapes and modeling. And so if we go through a whole bunch of different materials, we can develop these sort of models that mimic the peak shapes that are present. And we do it this way so that it gives you some leeway in how you fit these things. So everyone's spectrometer is not the same. Things will be taken at different resolutions. And so doing it this way allows you to loosen some constraints if you need, sort of, for say, for example, on full width half maxes of the very sharp peaks, you may not get as sharp a peak if your spectrometer is older or if you're using lower resolution settings. So these sorts of tables allow you to work with those sorts of issues, as opposed to just using a straight copy and paste of a spectrum, which is used in other systems, things like IR and those sorts of things. And so we do all this sort of stuff, and we set up these fitting routines, and we can go in and there's some times you have to play around with backgrounds. So for example, the Shirley background doesn't necessarily work perfectly for some of these systems because it's based on how much photoelectron yield is coming out. And so sometimes you have to do some things with offsets and those sorts of things to force the fitting of these things using an iterative approach. That's something you can get into by looking at some of the papers that we've written on this. But anyway, as you go through this curve fitting process, unknown samples, you can very easily and very, very accurately pull out how much of the different species that you have. So how much nickel metal, nickel oxide, nickel hydroxide. And again, we have a number of samples here showing all these changes in peak structures and shapes, and being able to pull out how much of the different elements or how much of the different species are present. And if we visualize that, you look at this, you go, well, it's a whole bunch of peaks just thrown under the curve. What does that mean? What we're doing is we're fitting whole spectra under these things, and this is not a new thing to do. This is used in other techniques as well. And so we've started promoting and say, okay, instead of showing our spectra like this in our publications, we tend to start doing it like this, where we've added all those peaks together to show the spectral envelope that we're fitting here. And that just seems to be, I think, a little easier for people to understand that that's what we're doing here. So now that we've pulled out that sort of information, well, what are some of the things that we can do with that? You can do depth analysis calculations. If you have a system where you can see the metal underneath and an overlying thin film oxide or hydroxide on that surface, you can use calculations such as those developed by Strohmeyer and Carlson that allow you to plug in the area under the curve. So say for the aluminum metal, you have so much under the curve, aluminum oxide under the curve, plug that in along with calculated inelastic mean free paths, and you can pull out and say, okay, I've got an oxide thickness of 3.7 nanometers. Great. Works well if you have just a single species or single type of overlayer. But if you have a mixed overlayer, the inelastic mean free path for nickel oxide is different from the inelastic mean free path of nickel hydroxide. And so you need to, what we've done is we've used kind of weighted values here where we plugged in all this data into this system, and this gives us an improved calculation of the thicknesses that you're going to get. And so in this case, we're able to plug in, we have so much oxide, so much hydroxide on a little bit of nickel metal showing through, and we get a film thickness of 6.2 nanometers. And we've developed calculators where you can plug these values in very easily, and it makes it, you can do a lot of different samples very quickly once you get it kind of plugged into an Excel spreadsheet for this sort of stuff. So we've done similar work for things like all the first row transition metals, manganese, iron, cobalt. With something like manganese, you've got manganese 2, manganese 3, manganese 4, manganese 6, and manganese 7 oxides, oxyhydroxides, plus other, carbonates and sulfates and all that sort of stuff. And all of them are going to have unique peak shapes, overlapping binding energies, some shake-up structures and things like that that you'll have to take into the model to pull out what you have. Cobalt's the same. Again, lots of different possibilities or different cobalt oxides, mixed oxide hydroxides, and then of course, sulfides and phosphates and et cetera, et cetera. One of the systems we looked at a lot was a stellite system, which is a cobalt chrome alloy. So there's mixed oxides there, cobalt and chrome alloys. And you have to model all those things in. So you're not just pulling out, okay, I have cobalt 2 or cobalt 3. It doesn't work that way. You've got to pull out what species you actually have for the most part to really understand what's going on in your systems. Iron is probably the worst of them all for curve fitting. You can have iron 2 and iron 3 species. You get a large variety. You got FeO, Fe3O4, Fe2O3, both alpha and gamma phases, FeOH, alpha and gamma and other phases, things like nickel ferrites, chromites, carbonates, sulfates, et cetera, et cetera. Each will have a unique multiplet structure and shake-up satellites. They're all going to have overlapping binding energies. They're all just iron 2 and iron 3, so they're not shifting a huge amount. So as the oxide and hydroxide mixtures grow in complexity, our ability to quantify or identify these species diminish very quickly. 2 species, very good analysis. 3 species, moderate to good. 4 or 5 more species, and you're really starting to push the limits of what you're able to pull out of these things. That being said, it does work reasonably well if you get good quality spectra, take lots of counts or take lots of scans to get good quality spectra. Be very meticulous about your curve fitting. You can pull up, how much iron metal versus Fe2O3 and Fe3O4 that you get. We have some comparisons here where we have the metal with FeOH, FeO, Fe2O3, slight changes in the chemistries, and we can see some changes in the amount of the different things that are present. And it made sense in the systems that we were looking at. So you look at these and go, well, that's a big mess of curves under this broad curve. How good could that really be? And so I don't know if I have that here. There's been some studies out of a group in Australia that shows that with the proper fitting, these things can be very quite accurate within a few percent of the actual amounts in a mixed species. If we look at how can we kind of push the limits once we get all this kind of data, if we use the combination of what we see in the high resolution spectra, so pulling out, how much copper 2 or chromium 3 oxide versus chromium 3 hydroxide we have, how much nickel oxide versus nickel hydroxide, and then we compare these to the analysis that we get out of our survey spectrum, we can do some math and figure out, how much of the different species are present, kind of broken down at the surface of a system. We've done that here for some C22 alloy, which has some thin film oxides on the surface, and it's been broken down. We've got so much the metals present, so nickel metal, chromium metal, molybdenous metal, and then the various oxides that are present as we change what we've done to this system. And for a variety of different electrochemistry has been done on these systems. And so that's one way to look at these things, and you kind of break down and say, oh, okay, we really have a lot of chromium hydroxide versus chromium oxide. So it's dominated by hydroxides, dominated or dominated by oxides, depending on what chemistry's been done. In this case, depth hasn't been taken into account. So these are just kind of the overall how much the different compositions of that surface that are present. If we start including depth effects, which can get very complicated very fast, you can really pull apart what you have at the surface of a thin layer on these sort of systems. So this was a nickel chromium molybdenum alloy oxide structure that we did something called Quasey's analysis on. And what Quasey's analysis does is it looks at the loss of the inelastic loss structures above the peak. So as a photoelectron is emitted, say an auction 1s photoelectron is emitted, it will come out with a kinetic energy of 890 or 900 and something. But if it comes from down here in this layer, it's got to go through all this layer to get out. And sometimes it doesn't make it. It bounces off and loses some energy. And so that's energy loss. So you can see these as you go up in the kinetic energy or go down up in binding energy of this spectrum, you get this more and more larger and larger background. And so that's loss that's going on. So these are a lot of background electrons that have lost energy that's in here. And so by analyzing that, you can figure out layering and figuring out depth of where these photoelectrons are coming from. And so you can put that all together along with what you've done with your survey scans, what you've done with your analysis, and we've been able to pull apart this oxide and hydroxide layer very effectively. And so we have our metal down here. We have a compact oxide, so something like some chromium oxide here. We have, as we go up more near the surface, we have a mix of oxide and hydroxide, chromium oxide and hydroxide up here, till we have nothing but hydroxide at the surface. And then within these layers, we've got molybdenum 4 oxide in discrete positions in this layer, and molybdenum 6 oxide in this layer. And so in this layer that is only 2.5, 3 nanometers thick, we've been able to elucidate exactly what that kind of layer looks like based on these types of analyses. Now, this is not an easy analysis. This was probably a year or so of Adam Morgan's work that he put in to try and pull all this kind of sort of stuff out, as well as doing things like depth profiling in top sims and Auger and those sorts of things as well. Angle resolve type analysis as well can get involved in this sort of things as well. And so it's a complex thing, but if your goal is to really pull apart what's going on at the surface of a system that you're looking at, these are the sorts of things that you can do. How are we for Auger parameter? The Auger process involves 3 steps. So you kick out a core photoelectron. You're using the photoelectric process. An electron from a higher orbital falls down almost immediately to fill that hole, and then excess energy of the excited state is removed by the ejection of an Auger electron. So again, you kick off a photoelectron, an electron drops down, and another electron gets kicked out. So it's a three-step process to produce an Auger electron. If you, and I won't go through this very much, but if you take the peak maximum of the Auger peak and use its kinetic energy, you add that to the binding energy of your core photoelectron peak, you get what's called the modified Auger parameter. And why do we want to do that? When you're looking at Auger structure, so this is a cadmium peak, you have to know which peak you're looking at. For example, we have the cadmium M5, N45, N45, and the cadmium M4, N45, N45. You have to know which peak you're using so that you can define which Auger peak that you're looking at. In this case, we actually use not the strongest peak, but the sharpest peak, which is the M4, N45, N45 peak, to calculate our Auger parameter. If we look at peaks for the cadmium 3D 5/2 peak, you can see we have a whole list of binding energies here. But there's actually not a lot of separation of these binding energies. So the total range of separation from everything from the metal on all through the different species is only 1.7 eV. And we have a large cluster of values around 4.5, 405 to 406 eV. And so being able to say, okay, what species do I have just from a specific binding energy becomes very difficult. There's just too much error in there to get really good speciation from just the core photoelectron peak. Whereas if we look at the Auger parameter, we now have a range of separation of almost 4.4 eV. So we've got a much bigger range of separation. So that allows us to clearly separate out different species a lot more easily. And so that's just another tool that we have that allows us to pull out what species that we have. Some further examples of all these sorts of things together. At Western here, we have quite a number of groups that are working on how we're going to bury our spent nuclear fuel underground for the next million years or so safely. The present system looks at using a big steel container that's clad in copper. And so we want to understand, what kind of corrosion, what kind of electrochemistry is going on, particularly with the copper, and how long is that going to last underground. If we look at different samples that have been exposed to different things or different electrochemistries that's being done, if we look at the copper 2p 3/2 peak, we see that peak looks the same for all these samples. And the reason that is because copper 1 species and copper metal basically all show this nice single peak that you can't really do anything with it. You can't get speciation out of that. However, if we look at the Auger peak, you can see we've got changes going on within these things. And so those changes are going to say, okay, well, maybe we can pull out these chemistries. So down here, we've got mostly copper 1. Up here, we've got mostly copper 0. And then here, we've got somewhere in between, sort of a mix. So we're going to look at those sorts of things and try and use those analyses. And so what we've done is we've done curve fitting of the Auger peak. And so that allows us to, again, semi-quantitatively or even fairly quantitatively pull out what species we have that we aren't able to do by looking at just the 2p spectra. We've developed this sort of things for a wide range of copper species, and there's a lot of information we can pull out of copper. For copper 2 species, we have that shake-up structure that I talked about earlier that means, okay, we've got copper 2. Copper 1 and copper metal don't show this structure. But you can look at that shake-up structure and see that it changes dramatically as we have different species present. So we actually use these spectra to do curve fitting procedures to say, okay, I've got so much in my copper 2 species, I'm seeing copper 2 chloride, I'm seeing copper 2 oxide, etc. For copper 1 species and for copper 2 species, we can also pull out the Auger spectra, which again, lots of changes in positioning of the main peak and lots of changes in the shape of that peak as well. And so we can use that we can look at modified Auger parameters just to kind of see if that helps us things out, especially for nickel or for copper 1 species. And we can do curve fitting to kind of pull out, overall what sort of things that we have. We have all sorts of tables and things like that. We've developed calculators that allow us to quantify using the shake-up structure how much copper 2 species versus copper 1 and copper 0 species. And then we've done a lot of curve fitting, as particularly the Auger peak, which has been very effective at pulling out what species we have. And so, for example, we've got so much copper metal, so much copper 1 oxide, and so much copper 1 sulfide. If you looked at the corresponding copper 2p spectrum, you'd have a single peak there with kind of no information coming out of that as to how much of these things you have. Whereas here we can pull out quantitatively or semi-quantitatively how much of the different species we have, those copper 1 species and copper 0 species that we have. This is the website that I've put together over the last 15 or so years. And so this is xpsfitting.com. You've probably seen most of this. A lot of you have probably used this. It's got a lot of this stuff available on how to do these things. There's videos and things like that that you can look at that will help you go through doing some of these complicated things, etc. I would like to take about a 10-minute break, and then I'm going to get into some of the submitted questions that we had. We had a lot of questions, so I've got them all categorized as to what we're going to look at. If we go through, we had 92 questions submitted by people, and so I used our friend ChatGPT to kind of go through and summarize what different things people were mostly interested in. Some of the big things were reliable peak fitting and deconvolution. I've talked about that quite a bit. Overlapping peaks and complex systems. We've gotten to some of that a little bit. Oxidation state identification. We've definitely gone through quite a bit of that. Talked a bit about quantitative accuracy. We can talk a little bit more about that. One of the big ones that I want to get into is energy referencing and carbon correction. There's been a lot of questions on that. There's been a lot of controversy in the literature recently, talking about why, whether we should be using carbon for charge corrections and those sorts of things. So we want to talk about that. Things like background selection and fitting. We've touched on that a little bit, so I'll get into a little bit more about that. Charging effects, again, we'll talk about that. Surface sensitivity and depth information, I've gone through that, things like Quasis analysis, angle resolved analysis, calculations for simple oxides on metal surfaces. And then also we'll talk a bit about oxygen peak interpretation, and then if we have some time, we can talk about standards and reviewers and things like that. One of the first ones I want to talk about is background selections for fitting parameters. So, a lot of the questions were, why do we use the background that we do use? There are 3 common backgrounds that are kind of in use. We have a linear background, which is just a straight line, a Shirley background, and what's called the Tugard background, developed by Sven Tugard out of Denmark. So for a straight line or linear background, some of the problems it suffers from, you can get large peak area changes depending on the position of the endpoints. So if you think you have a starting baseline endpoint down here and an ending baseline endpoint up here, as you change the positioning of that background along that, you get these huge area changes depending on where that endpoints are. So it's not a very accurate thing to use unless you have basically straight background that's basically starts here and ends here kind of straight across, so it turns out linear regardless of what your background that you use anyway. So I would avoid using a linear background for all but maybe the most seldom case. The Shirley background was developed. It it's a purely mathematical background. It was developed as the background goes up in proportion to the total number of photoelectrons below it in the binding energy position. And this is what was used for many, 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 many years. There wasn't a lot of other backgrounds that had been developed. Um, way, 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 way better than a linear background. Not quite as technically as accurate as a two-guard background, but its ease of use has resulted in its widespread adoption. And for most scenarios, you don't need to go much past the Shirley background. It will do the job more than well enough for most cases. Um, uh, the two-guard background or two-guard universal cross-section approach is a methodology for integrating the intensity of the background at a given binding energy from the spectral intensities to higher kinetic energies. Is very accurate in modeling what's going on in the inelastic all the loss structure and inelastic backgrounds that are going on. For real usage to really take advantage of its accuracy, you need to use a much larger window of analysis on the higher binding energy side of the peak. And so instead of that standard window that you're working with for that's kind of pops up on most instruments, you need to go much higher to really take advantage of all that intrinsic signal that's present. So 30 to 50 EV above the main peak. It is the most accurate, but it can suffer from complications in practical use, particularly if you have a lot of elements in your system and you get a lot of peak overlaps. It kind of falls and it doesn't work as well. And so if you really need to push accuracy, um, your two guards your way to go. But again, for ease of use and for most general applications, the Shirley background still has a lot of uses. The Shirley background can give you issues if you have really high jumps in your background, say from low to high in a complicated peak shape. There's going to be some issues. You may have to do some changes in your background positioning, and I talk about that in some of the papers, especially on nickel, how we have to make that work. Um, um, but there are kind of things that you can do to work around that. If we look at this is a nice publication that came out just recently from Dick Brundle, Vincent Christ, and Paul Bagas, where they looked at, if we were looking at iron samples or gold samples or things like that, how good is the quantification using the different backgrounds present? And again, as not suspected or not unsuspected, the linear just doesn't do the job properly at all. So don't use a linear background. There were really only marginal quantitative differences between the Shirley and the two-guard background usage. And so, particularly for survey type spectra, the biggest error is not using consistent baseline endpoints. So that baseline endpoint between the start and the end. And you can see as you change endpoints, no matter what background you use, the area under the curve will change significantly if you have an endpoint here versus an endpoint here. Doesn't matter whether you're using two-guard, Shirley, or linear. Those changes in that background positioning is going to affect things way more. And so what they found that you needed to really use especially if you're comparing materials, you needed to use the same background endpoints to make things work, to make comparisons look useful, to even get, semi-quantitative data that really mimics what you have. So if you have so much iron versus so much oxygen, there should be a certain ratio if you believe you have Fe3O4 or Fe2O3, or even if there's other species present. The ratios in your survey spectra should follow stoichiometry reasonably well if you're doing this quantification right. And so again, there was very marginal differences between the Shirley and the two-guard background. Again, there was those positioning of those endpoints is what mattered more than anything. And so you need to think about that when you're doing your analysis. And it wasn't just the window size on each element. It should be each window should have. So if you're doing a 20 EV window in your backgrounds for the iron, you should be doing the same thing with your oxygen. You should be doing the same thing with your carbon. How much changes that's going to make? Again, it's got to be consistency is more important, especially if you're comparing a whole bunch of different samples. Consistently do the same thing over and over again so that the comparison between those samples are meaningful. If you're really trying to get accurate, okay, I need to know exactly how much oxygen or how much sulfur versus your iron or sulfur versus your nickel is, you need to figure those things out. Then you nearly start thinking about, okay, now should I be using the Shirley or two guard, of where are my endpoints going to be? Those sorts of things can then come into play. But for most general work, again, the Shirley background does work just fine in comparison to the two guard background. So going to those extra steps may not necessarily be necessary. So it's a trade-off, right? In any analysis, the time taken, the ease of use, how much do you get? Do you increase your accuracy by, you know, a 1/4%, or are you increasing your accuracy by 10%? Well, you need to decide what steps you need to go through to increase those accuracy. And from the work we've done, on transition metals and things like that, it's generally good enough to know if I've got 30% nickel oxide, 50% nickel hydroxide, remainder metal. I don't need it to be 50.03, or, there's a trade-off as to how accurate you can get and whether it's worth putting that extra time in. Sometimes it is, but it's not necessary for most things. Energy referencing and carbon correction. This is a pet project of mine, and charging effects. So charge correction. So we talked about a little of this before. If a sample is charging or it's insulating, the action of the charge neutralizer will shift all species down, 2 to 3 EV is generally what we see. And so therefore we need to have a charge correction method so that we can have an energy reference so we know what we're looking at. Number of things that you can do. You can charge correct to adventitious carbon at 284.8 EV, and that's the aliphitic line of the adventitious carbon, not the peak maximum. You have to find out where the aliphitic line is, because that's what we're correcting to. If it's an organic species, if it's not adventitious carbon, if it's an organic material, you need to figure out, okay, well, what is my aliphitic peak, or something in reference to that. If you have graphite present, that's a different charge correction. So that's not the same charge correction. It's not the same material. So charge correcting to a graphitic peak, doable as well. We do it here, but it's not at 284.8 anymore. It's 284.5. If we look at adventitious carbon as a charge reference, again, we're going to do a curve fitting of the carbon 1s peak, and these are kind of like a standard setup of a curve fitting where we have our carbon main peak, carbon oxygen, carbon doubly bound oxygen, etc. These peaks are going to be at specific positions. We've set all these peaks to have the same full width half max, and then we've pulled out where that peak was, and we do that charge correction as I showed you earlier on in CATS XPS. We need to fit that carbon 1s spectrum consistently. You can't just throw a whole bunch of peaks into there. You do have to really kind of think about what the chemistries there are, general chemistries. And again, I talk about, we'll have the main peak. We're going to have another peak constrained to be about 1.5 EV above the main peak, and that's our carbon singly bound to oxygen with an equal full width half max to the main peak. We'll have further peaks that can be there, ketones or other functionality. We're going to have carbonates sometimes present, and we may have to put those peaks in, and they may or may not have to have their full width half maxes constrained if they're not if they're only poorly resolved. Note that this is not for polymeric samples. If you have a polymer on your surface, or you put some organic material on the surface, that's no longer adventitious carbon that you're fitting. But the aliphitic peak of those polymers, if it's there, or of that organic material, if it's there, and it may not be there, like if you have ring structures or lots of double bonds or lots of other things, you may not have aliphatic carbon in that spectrum. And so you cannot charge correct to an aliphatic peak in that spectrum if you do not have it there. But if you have it there and you kind of know what it is, you can fit that, and that aliphatic peak should be at 284.8 type of spacing. Some of the biggest problems we see are differential charging. And I talked about this a little bit earlier. You can have, say, a background of a semiconductor or a metallic species with thicker or thinner bits of contamination, oxide structures. Maybe you've got some built structures that you've put on there that behave differently. They're not conductive or they are conductive. You've got conductive stuff on the background of a non-conductive species, etc. So all these things are not in the same, behaving electrically the same, especially if that sample holder or that sample is attached to grounded to the holder of the system. And so the apparent positioning of all those things can change. And so you get split peaks and things based on the fact that things aren't conductively behaving the same conductively, even though they're chemically the same. You can also see this in layers. So if we have like a metal surface, we've got this interlayer here that if this was a thin enough oxide, it would behave almost conductively, and you wouldn't even need to use a charge correction system on this. As that layer grows, it becomes insulative and it no longer behaves in conjunction with the metal, which is pegged at the Fermi level, right? As you put layers on top, things change. Some of these layers may not behave the same as others. And so you get this differential charging problem. One of the ways to work around this is to electrically isolate or float the entire sample. So there's no conductive path to the holder. And you can do this by putting on a glass slide or on double-sided non-conductive adhesive. Generally works well for powders, mineral samples. We do all sorts of materials now, even things that are metallic, have underlying metallic samples. We generally do a lot of our work now with the samples electrically isolated and use the charge neutralizer to get things to work. Excuse me. So adventitious carbon. And this is where some of this comes from. There's a group out of Sweden, Gregor Grzinski and Lars Hultman, that have put forward a number of papers talking about how adventitious carbon, we shouldn't be using it. It doesn't work. They've got when they first started, it was some fairly sensationalistic titles that came out. Things like compromising science by ignorant instrument calibration, a need to revisit half a century of published XPS data. I have to say it did ruffle some feathers in the XPS community, particularly myself. I just didn't, it didn't jive with what my experience was. And again, I have now 30 plus years of XPS experience, probably about 33 years of XPS experience now. And we've been using adventitious carbon effectively for thousands and thousands and thousands of samples running on instruments that we've been able to make that work and make that charge reference work, that we were able to pull out chemistry routinely and effectively and corroborated by other instruments and corroborated by what it should be in other science techniques. And so for someone to say, you need to throw out all this data, you can't use it, doesn't work, it did not really jive at all with my experience. And so, well, how do I refute that? How do I take these claims and go, okay, well, that's not really what's happening. Yes, there are problems with the technique for those who don't use it properly and don't understand it, and we need to fix that for sure. And so, but in my experience, it was not accurate to say, we need to get rid of all this data and it was all garbage. And so the first thing I did is I went through, a multi-user facility. So I went and looked back 5 years worth of XPS data that I had personally taken from samples that came from Western University, other universities across Canada and the United States, as well as industrial clients from Canada and the United States. And we had a breakdown of samples over here from where they came from. The types of samples, we looked at all sorts of different types of samples. We had a broad survey. We had polymeric samples. We had powders, inorganic powders, organic powders. We had a bunch of thin film stuff. We had things like inorganic solids, including battery technology work, semiconductor, electronics. We had catalysts. We had a lot of stuff from metals and corrosion and thin films and corrosion products, things like graphites and graphenes and carbon nanotubes. Lots of different types of materials that we looked at. And then we looked at, well, what, 62% were insulating by nature. About 33% were a mix. So they had insulating properties and conductive properties. Only about 5% of the samples that we looked at were fully conductive in nature. So that's a small amount that's available for that type of analysis. And we looked at, what kind of charge referencing we use, whether we needed charge referencing or not. So no correction aligned with the Fermi level. Those are those things that are fully conductive. And so they align. We got a nice Fermi level. Spectrometer calibration is great. We can get a very exact analysis of, where a graphite peak is or where a metal peak is very, very easily. Sometimes we've done for charge correction for adventitious carbon, over 500 of those samples we used adventitious carbon. A lot of those samples were polymeric or organic in nature. And so while we were charge correcting to a carbon-hydrogen alkyl peak, it's not adventitious carbon that we were charge correcting to. So it's a difference there. It's not the same thing. Same with polymers. So we had a lot of the polymers and stuff like that. We had a lot of samples that were graphitic in nature. And so we weren't, again, not charge correcting to aliphitic carbon. We were charging to graphitic carbon, which is a different charge referencing number. And sometimes we were able to use other internal peaks as well. And we said, okay, well, we want to make sure we have, standardized curve fitting procedures for the carbon peak. And so we've got presented different standardized curve fitting procedures for, say, graphitic materials. We want to fit this very consistently in order to get the right values and the right amounts of the different, if you've got graphitic oxides or graphene oxides or things like that, or carbon nanotubes or a similar looking sort of thing that will have, functionality put on them. So we have fitting procedures for that. And we also have a fitting procedure for our adventitious carbon so that we're fitting that consistently so that we're getting the right value for and right positioning of that carbon-hydrogen peak. And these are just some examples of graphite-like materials and how you can, that curve fitting, same curve fitting parameters for all that gives you different values of the amounts of different oxygen type species that are present on those samples. Again, then for adventitious carbon, these are the same fitting parameters, and you can see how the carbon, it does change. It kind of moves around a little bit. You get more or less oxygen sticking on different surfaces and stuff like that, more or less oxygen components that are on there. If we looked at the positioning of this high-end peak, we looked at that position and how that changes. We looked at those sorts of things, trying to understand, what the adventitious carbon looks like. And then we looked at, where's that positioning? If we were able if there was a secondary charge reference available, what is the position using that secondary charge reference? So say there's a metallic peak in a floated sample or a well-known peak for something. How does that say, okay, well, where is that carbon really sitting at? And so we found with this data set, we were getting a peak position of about 284.91 with standard deviation of 0.25 EV for the peak position for the aliphitic carbon. The big result was, well, how good does the adventitious carbon charge referencing technique work? And how did you judge that? Well, we judged that by, did we get results that were consistent? Did they make sense? Were they backed up by other things? Did it make sense with all the other peaks go and you were able to say, okay, I could pull out relatively easily a good chemistry for this sample. And so for the 522 samples from this study, we found that we had about a 95% success rate using adventitious carbon as a charge reference. And so if I were to say to you, you know, I got a cure for a certain type of cancer that was 95% success rate, you would be jumping in the streets and very happy about that. And, you know, you wouldn't be saying, oh, we can't use that. The 5% failure rate is no good, right? Like you just throw it all out. So you wouldn't be saying that. Some of the things you've got to look at, it's got to be adventitious carbon. It's not graphitic materials. It's not polymers. It's not organic components. It's not carbon from silicon. We do need to choose and report a consistent binding energy for adventitious carbon. That's a problem in the literature. We can use a secondary checks of binding energies of position to confirm your results, which is always a good idea. If you can confirm your results using other peaks, great. A range of plus minus 0.2, 0.3 is generally sufficient for most chemical state analyses. If you're trying to get tighter than that, then you need to start looking at things like using the modified Auger parameter or looking at peak shapes if that's available. So there's other ways you can get around these sorts of things. The biggest issue that we found for samples, the 5% that failed, was differential charging. And so it's not necessarily a failure of the adventitious carbon, it's a failure of our ability to either mount those samples isolated or make them behave properly, where if you change, you know, things are moving around. And so differential charging was the biggest problem. And sometimes that's just something that can't be avoided, you know, if you can't ground or you can't float the sample, or there's other issues like that. So that was the biggest problem that we found. So we looked at some further work. Some of the concerns that come up in some of the papers from Gregorz and Holzman were concerns about consistency and usage of the charge correction. That's the previous study kind of shows that. One of the things was they pointed out, well, how can we use adventitious carbon if we don't really know what it is? You know, there's really only been one study that looked at what it really is. There were many assumptions that have been error from older literature, things like, oh, it was pump oil or it was graphitic in nature. You know, what is its origin? What's its origin? And we kind of intuitively understood it. You know, it was from volatile organic constituents from atmosphere, both in general and affected by local conditions. So if you have different volatile organic compounds floating around, those things are going to stick to the surface of these materials. And so, okay, well, we'll answer those questions. And so we went and did a fairly large study where we looked at a whole bunch of different sample surfaces and tried to understand what's on there. We looked at what sources are possible. So, you know, well, what is in the air that could get onto your surface? And it's not going to be big molecules. It's going to be short stuff. So, you know, what volatile organic components are in the air? And they have certain partial pressures and those sorts of things that are available. They're going to have different sticking coefficients. They're going to have different, you know, larger, more carbon is, you know, there's not going to be as many of them. Different partial pressures. One of the things that we thought about a lot is how does the effect of beta shifted carbons affect the positioning or the apparent positioning using our standard fitting, the apparent positioning of the carbon-hydrogen peak. And so what is a beta shifted carbon? And so if we look at this carbon here is directly bound to an oxygen. And so that's our primary. It's going to shift that binding energy position of that carbon up around 1.5 eV from the standard alkyl position. These guys here, these three, they look like they're alkyl, but they're actually not. They're alkyl that have a shift to them because of the effect through this carbon to here. And they're going to shift up, you know, 0.1, 0.2 eV. So it's no longer, this is not alkyl carbon. This is a beta shifted alkyl carbon. And so that's adding error to the position of where that alkyl peak is using our standard fitting. And so if we take those sort of things into account, well, first we also looked at, what does the adventitious carbon look like? We did some whole bunch of averaging of different spectra. So this is what an average of 80 adventitious carbon spectra look like. And it's carbon with some carbon bound to oxygen, generally around 25% carbon functionality bound to oxygen. If we look at TOF SIMS, which is another technique that can look at this adventitious carbon, we actually use adventitious carbon fragments to calibrate our TOF SIMS spectra. You can see we've got so much, just a small fragmentation pattern, not a lot of very large fragments. It dries off very quickly. We have some oxygen components as well in the positive ion spectra. And so, again, this reiterates this thought that these are short chain volatile organic components that are sitting and sticking onto these surfaces. If I go back to that beta shift problem, as you add more oxygen in your adventitious carbon, so up here we have a lot of oxygen species, the positioning of that main peak shifts. So if we have very little adventitious or oxygen in that, there's the alkane peak and the peak maximum of that main peak are very close together. They're going to be about 284.8 bang on. As you add oxygen, these beta shifts moves the apparent position of that peak maximum over quite a bit. And it can be over as much as 0.3, 0.4 EV. And so that's a lot of error that you're adding into that if you just use a peak maximum or your standard curve fitting compared to including these beta shifts effects. And so when we did that and using data from the previous model, we were able to find that aliphatic peak was at 284.81, 284.8 EV plus minus 0.25 EV was found. And so that 284.8 binding energy for that alkane peak that's been suggested by others in the past is looking at just alkanes and things like that. Again, for adventitious carbon, that's what we want to be using, I think. So some conclusions from that, we found, it's on average adventitious carbon aliphatic in nature with about 25% of oxygen associated with it. It is not graphitic in nature. We did some work by deep parameter work and TOF SIMS work that showed that. And if we use a peak fitting model for ADC that includes the beta shifted peaks, we can remove some of the error in that peak positioning. And we found an aliphatic peak binding energy of 2084.8. So go back to the work from Grzinski and compare it to what we've done. So he says, and he keeps saying, he's a prolific publisher. He's now published, I don't know, 8 or so or 9 papers that are kind of all saying the same sort of thing using different methodologies and things like that. The problem is he's coming at it from an angle that it's like throwing out the baby with the bathwater is what I'm saying. He says there are some problems with the adventitious carbon charge correction method, and we should just stop using it. He says things like it's through 50 years of data suspect, calls this method least accurate, etc. So again, I disagree. We've done a study for 5 years of data that shows a very high success rate. A second study was done again with from another broad user facility in England from David Morgan, who went through 5 years of data as well, and he says, but for a few exceptions where the secondary reference is preferable, an adventitious carbon value of 284.8 is suitable for electronically isolated samples, which is kind of exactly what I'm saying. So he's also agreeing. It's like, look, this doesn't match up with what we're seeing in the real world, that it does work. He says, we don't know what ADC is, so how can we use it? How can we trust it? Fair point. Somewhat misleading. Barr in 1995 did a study and showed, basically what we found, that it's mostly polymeric hydrocarbon species with minor components, 10 to 30% of the total signal being oxygen based as well. So we've done that as well. We've done XPS and top sims. Yes, it's not graphitic. It's mainly short chain hydrocarbon species, which is about 25% oxygen. Older reports say it's pump oil, graphitic hydrocarbons. Take that with, that's how science works. In the old days, someone postulated something, someone proves it's wrong, we move on. So to say, okay, in the old days, they said it was this, they said it was this, they said it was this. Sure. But we now know now, and actually in 95, we probably had it pretty much figured out that it's, volatile organic components from the atmosphere, these short chain hydrocarbons, etc. So I think we've answered that question. So we can't really beat on that anymore that we don't know what ADC is. I think we have a pretty good idea what it is from just these two studies alone. Arbitrary setting of the adventitious carbon 1s peak. We've seen ranges in the literature from 284 to 285.2. 100% agree. 100% agree with him on this. If we're going to use a reference, we have to use the same number. Everyone has to use the same number. Some of that problem is that people are I don't know, they're just making stuff up or doing, I don't know where they're getting those numbers from. The NIST database itself suggests 284.8 for the alkyl portion of the ADC as the correct value, as others have stated this in the past, that 284.8 EV is the right number for this value. We have to use it. You can't just make your own number. We have to use the number. We have to use a consistent number. Otherwise, referencing doesn't work. So totally agree with him on this case, that we have to pick a number. We have to use this number. ADC aligns with the vacuum level and not the Fermi level. So it cannot give us the correct binding energies. I agree and I disagree. We have to realize that these are two different referencing systems. If you have the Fermi level available and you are working with a conductive material, then absolutely we need to use the Fermi level. If you're going to get an exact number, if your gold value, you're setting your system to set the gold metal should be at 83.96 EV. Your Fermi level will be at 0 then. We can get very, very accurate results for conductive materials. Very accurate. Not so with insulating samples. We don't have a Fermi level. If you look at an insulating sample, you don't see the Fermi level. It's not there. And so we can't use it. How can we use that? Well, you've got a metal peak in there, but how do you know if they're connected? If you've got an insulator and a non-insulator, they're not behaving the same way. So if we float the samples, you're going to use adventitious carbon as your charge correction. If you have a metallic peak in there, it may not be exactly where that metallic peak is there, because this is not, again, it's not the same referencing system, but we don't have really an alternative. So as long as we know what we're doing and as long as we know what we're referencing to, and everyone's referencing to the same number, then if I look at a system that has, magnesium sulfate or something on the surface, and I'm referencing to adventitious carbon, and I get a number for the sulfate of 169.8, you put that in your system, do the exact same thing as I do, probably going to get a pretty similar result. And you're going to be able to figure out, yep, I got a sulfate. Great, that's what we want to know. And so having that, the correct binding energy, what does that mean? As long as you're referencing to the same thing, and when you're reporting, you're saying, okay, I'm reporting to adventitious carbon at 284.8, the aliphatic peak of that, then it works. And so these are two different referencing systems, and we have to accept that because we really don't have an alternative for insulating samples. There's not one that's universally easily accessible, but we have to do it correctly every time. We have to think about how it can fail and how we can make sure that it doesn't fail when we use it. We have to think about getting the best positioning of that alkane peak, and then getting rid of those errors takes away a lot of the failures that occur. And so a lot of the things maybe he's seen where it's failing are because of other issues as well. particularly if you're not using the same number for charge referencing. So some of the ways to look at this, if I look at the Fermi level versus ADC referencing, if I look at zirconium oxide references from the NIST database, there was 21 references. You get a binding energy value of 182.6 eV with a standard deviation of 0.6 eV for all zirconium oxide samples. If I look more closely at those samples and I see references that are listing either gold as a reference value or a conductive sample, so like a thin film oxide on a metal, those are 8 references, we get a binding energy of 182.8 eV. If I look at the bulk zirconium oxide listing the aliphatic component of AdC as a charge reference, we get a binding energy of 182.4 eV. So now you can see how these are 2 different references based on what kind of samples you have. We can do similar things. Aluminum's one that really sticks out like a sore thumb. Thin film aluminum oxide versus bulk oxide. It's a difference of 0.7 or 0.8 eV between the 2 references, but they're different references and it's very consistent. It's almost a bimodal referencing you see for these things. One where it's referenced to the metal in a conductive thin film, and one where it's referenced to bulk oxide where there's no conductive material available. Magnesium does the same sort of thing. And so you have to think about what you're analyzing. Are you looking at a thin film where you can do this kind of Fermi level referencing? Or are you looking at a bulk oxide? And those are the sorts of things that we look at. And so that's my rebuke to the fact that I keep seeing people say, "Oh, you can't use adventitious carbon. It's a no-no." They're wrong. In my opinion, they're just dead wrong, and in other people's opinion as well. But it has to be used correctly, and you have to understand it. And that was another argument he made. It's like, well, it's too complicated for people. You're scientists, figure it out, right? Like that's a lame excuse. I've seen that kind of stuff. So, all right, that's my rant on adventitious carbon. Thank you for joining my TED Talk. I appreciate it. If we look at the oxygen peak, that was another big question that we wanted to look at. Oxygen can have a lot of sources, and people get focused on kind of if they're say, "Oh, I'm interested. I'm looking at cobalt oxides, so I want to look at the oxygen peak." But then they don't realize that they have other sources of oxygen available in their sample that are contributing to the oxygen peak. And so with oxygen, you can get a huge range of organic and inorganic oxygen containing species. It can come from multiple sources, not all of which are associated with your elements of interest. What do I mean by that? So this is I believe it was a titanium or an apatite type sample that a whole bunch of different species on the surface. And they were interested in we wanted to know from the survey spectra how things were changing. They wanted to look at the oxygen to titanium ratio. It's a good way of looking at things. And so when you first look at this, you just plug in the numbers and go, I got so much titanium, so much oxygen, and I get a ratio of 2.36. It's like, well, okay. But that's not really true because there's oxygen also associated with carbon. There's oxygen associated with the zinc. There's oxygen associated with the silver, silicon. There could even be water present as well, which we want to know about. And so that number is wrong. And so we got to remove the influence of oxygen from other species in order to make that kind of calculation work. And so if you do high resolution spectroscopy to understand the species that are present, you can then factor these sort of things out. So the zinc that was present is a zinc oxide, 1-to-1 ratio. Silicon was present as a silicone, again, a 1-to-1 ratio, and silver as silver 2 oxide, again, a 1-to-1 ratio. And so you can factor those things out. And when you do that, you get a more appropriate titanium to oxygen ratio because now you're just looking at oxygen that can only be associated with the titanium. One of the things that is hard to figure out is the oxygen that's associated with carbon. And so we've developed calculations or calculators that allow us to go in, do our curve fitting of our carbon 1s peak, and we have carbon bound to the different species here. Take those things, plug it into this calculator, and it's going to calculate the amount of oxygen that is present that's associated with the carbon based on the chemistries that we see here. And there's a whole bunch of caveats in how you do it and understanding of what's there. You know, if you've got carbonate, you can plug that kind of values in. But you can pull out how much of the carbon in the survey spectrum or how much of the oxygen in the survey spectrum is from carbonaceous oxygen, how much in that oxygen spectrum is percentage-wise is due to that. And so that'll really allows you to improve your analysis of the oxygen 1s spectrum. And so that's how we've done that here, doing these correctly adjusted titanium oxides things. If we look at kind of standard curve fitting of an oxygen peak, like if we look at something like nickel oxide, you get this main peak, this main lattice peak. That's what you would call your typical oxide. A lot of times you're going to see these higher binding energy peaks as well. And so some of this is going to be from adventitious carbon, and you can calculate that. A lot of the time, this peak still has structure. It can be a little bit of surface hydroxides. It can also be defective oxide. So you have within your lattice structure oxygen that's got more or missing vacancies of nickel or missing things or just defective edge locations and weird sorts of defects that can cause that oxygen peak to have a higher binding energy. It's still part of that kind of lattice oxide, but we call this defective oxide. But it can vary, and it really depends on how that material is treated and those sorts of things. When you're doing curve fitting of these things, you want to watch your full width half maximums. You can see how in this cobalt oxide system, we've got this main peak and then this defective oxide or other thing. And this thing's been heated to 1900 degrees Fahrenheit, so it's very unlikely that there's much adventitious carbon left on that surface, depending on how clean the surface is, or there's very unlikely that there's a lot of hydroxides present, that's for sure. So this still might be some defective oxide, but you can see how this peak is really broad. And so it's kind of stealing peak area from this main peak. Like this main peak really should be up here. And so you got to put some constraints on. You can't let this peak get too broad. So you kind of put some constraints on the thickness of this peak. Otherwise, you're really not getting the true picture here. You know, this peak should really fit this envelope very closely. And then this peak should be narrower so that it more precisely is more accurate about how much of that defective oxide or hydroxide is actually present. So those are some kind of a pitfall that you can get into. We have lots of tables for common oxygen values. Again, look at your survey spectrum. Don't get focused in it's just nickel oxide. But in your survey spectrum, you've also got, I've got copper oxide, I've got iron oxide that would also come into this same spot. You have to think about what other species could be present. Organic species, we have tables for where the various organic species would be, and you can fit those sorts of things in. If we kind of look at a generic fitting of a metal oxide, hydroxide, I usually have a lattice oxide, which is generally a little narrower than the hydroxides and other organic components. I usually fit this peak and this peak I constrain them to have the same full width half max. That generally works out very well. But again, in a system like this, you also have to look at and say, okay, I have these species, but what else might be present? And so I've got organic oxygen that could be in this area here. If there's silicon present or silicone present, that's going to be at a certain binding energy, and you may want to factor that in. And you can actually, if you've got the survey spectrum and you know what it is, you can actually do some calculations, say, okay, of that oxygen peak, I have so much silicon. I have, 5% silicon in my survey spectrum, and I know it's silicon dioxide. So therefore, 10 atomic percent of my in the survey scan of the oxygen should be silicon dioxide. I have a 60% oxygen peak in the survey spectrum. 10 out of 60 is silicon dioxide. So many percent, I can fit that in constrain it and say, okay, I know I've got, you know, so much percent of this peak is silicon dioxide. And you can do that for other things. Aluminum sulfate's another one. You see a little tiny sulfur peak, but you times that by 4. If it's sulfate, it's a lot of oxygen that shows up in that oxygen peak. So those are the sorts of things you can think about as you're looking at that oxygen peak. That's kind of what I had prepared for the day. I don't know if there's any, we've got a whole bunch of stuff in the chat. I don't know if there's some questions in there or not. I'll take a quick peek through.
Yes, yeah, there were some questions in the chat.
Da, da, da. Yes, here's a good one. Kindly comment on the stability of nickel-3 states you mentioned in your paper, like beta, NaOH, and those sorts of things, gamma NaOH. Are they all stable, and possibly under what conditions are they stable? So we've been looking at nickel for a long, long time. We've made nickel-3 species that we've analyzed in order to get those standard spectra. To see nickel-3 in the real world is actually pretty rare. Um, a lot rarer than what you would see in some of the literature. And what happens is, and if I can go back to, let's see, escape here, just go back to my screen here, and I'm going to go back to our nickel spectra. So we've got our nickel spectra. And if I go down, so there's our gamma NaOH, that's a nickel-3 species. What we're seeing a lot in the literature, far too often in the literature, this kind of talks about your question, is we will see a spectrum that looks like nickel oxide, maybe a little bit of nickel hydroxide, and they will have labeled that this peak is nickel 2 and this peak is nickel 3. And based on that, they have their whole paper, might be based on the fact that they're seeing nickel 3. And I've seen this a lot in battery technology papers where they're talking about, they've got nickel 3 present. When really they do not have nickel 3 there probably at all, or it's only there in the tiniest amount, when really all they have is nickel 2 oxide. And so that's something to watch for. The amount of times that we've been able to pull out nickel 3 and only seeing it through very, very controlled experiments where we're trying to see in situ thin film growth on nickel metal, the growth mechanism that is postulated to have some nickel 3 production first before the nickel 2 proceeds or something like that. It's been a while since I thought about that. But being able to pull out that nickel 3 amount in that oxidation process, and so usually only a small amount, it's not something we see a lot of. And so I've seen a lot of nickel samples where do we have nickel 3? Do we have nickel 3? And generally it's like, nope, you have pure nickel 2 oxide, mix of nickel 2 oxide and hydroxide, stuff like that with some metal underneath. So I don't know how that relates to the question about, how stable are these things. I mean, if you make nickel 3, it was stable enough that we were able to get a good analysis of it. I don't know how long it, if it eventually decomposes or whatever. I don't really know that kind of stuff. But I know I don't see it a lot in real world samples when I do the analysis. It's just very uncommon for me to see a nickel 3 species showing up. So I hope that answers the question. Let's see, for FE 20, FE, no, let's see here. For Fe2P3 fitting, I've noticed the model struggles to differentiate between FeOOH and Fe2O3. At the same time, I don't really know to what extent the system can truly differentiate between FeO and Fe3O4. So there's some papers recently published by Tony Hughes out of Australia, Chris Easton, myself as well, where they went and they looked at how well these things work, these curve fitting procedures work. When we first did this work, when Andrew Grosvenor first actually looked at these metal samples, this was before we had a gas cluster ion source that could clean these surfaces. And so our FeO sample has some slight contamination of Fe3O4 on it. And it turns out that that makes a big difference. And so they've developed, and it's on the website now, these new updated fitting parameters for FeO and a little bit for Fe3O4 and a little bit for, I think, FeOOH that have improved the fitting because they were actually able to get better standard spectra because they could clean the FeO samples or the other samples in situ using a gas cluster ion source that gave them just a little bit better spectra, a little purer spectra. And it did make a difference to allow you to get better quantification of these things. And so I'd have a look at those papers showing how those things work. Where the modeling can also break down is the amount of metal that's present. And so when you only have small amounts of the iron metal, that metal peak and that large asymmetric tail can start causing problems because there's a lot of overlap there. And so the model cannot necessarily handle it because that information can no longer be extracted when you add more and more metal into the system. So that can be a problem. Like I say, iron is probably the toughest one to do. And then so there's some caveats there, and you really need to kind of go through some of the literature to pull that out. But these latest papers, and they're on the website, you can get the referencing, the details for those papers that will allow you to take a look at some of that sort of stuff, what some of the limitations look like. Let's see where we had. Those Fe2 mixed composition spectra were made with thin film samples. We've done both. We've done powders, we've done thin film, we've done, the works for all of it. It doesn't have to be thin film samples. We've done bulk corrosion products. We've done powdered stuff. We've done particles and all sorts of things. So yeah, it works for all of it. Can Quasis analysis be applied to nanoparticles? I don't know if the Quasis analysis works. There are models using the more kind of the calculations that I showed before that take into account the spherical nature of particles. So if you have a circle, the inelastic mean free path coming from here is different from it's like angle resolved on that surface of that circle. So it changes the math. And there are some papers out there that have gone in and gone through that math where they can look at nanoparticles of different sizes and understand layering based on those sorts of calculations. But it has to take into account that curvature of those particles on average. Yeah, there are papers, the people that have done that. I have papers somewhere that kind of, so I can't remember who had done that, but those things are available. Why do we look at the sharpest peak in the Auger and not the maximum peak? Is there any particular reason for that? Yes, there is. Sometimes that peak maximum is kind of multiple peaks that move around, just like I showed all those different Auger peaks that have different shapes. So sometimes those certain Augers have a whole bunch of stuff going on that peak shape for certain species is not really that maximum is not definable, whereas a different peak may have a much more uniform or more sharp peak that's definable. It's situation dependent. So they kind of go through and look at a bunch of different standards and say, okay, which one's going to work consistently? And it's not always the same one. Process, plotting these figures and explain how to use the software. The software, I mean, if you want to get into the software, there's some good courses that are being offered. John Grant down in the States offers a great course, 3-day course on using something like CAS XPS software. Manufacturers sometimes have them. Neil Farley, who wrote this CAS XPS software, sometimes they do workshops. I've been a part of some of those as well, where they show you the ins and outs of using that. Uh, on my website, I've got the basics covered, but if you want to get into the really like, it's a very powerful, some very powerful things that you can do in that software, but it's a whole another 3-day, 5-day course to get into that kind of stuff. Yes. What do I think about the FE3P fitting using parameters proposed in Yamashita paper in Applied Surface Science 2008 instead of the FE2P fitting for ultra-thin monolayers with mixtures? Um, I know I looked at it at that paper and tried to make it work. I didn't find it. I don't know how well it works. I'm not saying it doesn't work. I think from what I recall, it's kind of a FE2 versus how much FE3 type of calculation, which is fine. It may work for oxides. I don't know if it works for other species. I don't have an answer for that. Um, I do know there's another paper out there that talks about looking at the separation in the manganese, the 3s peak. So there'd be multiple splitting, then there's separation of the two peaks and the manganese 2s or 3s peak, sorry, that I don't think works very well compared to the fitting of the 2p peak. Um, it works okay if it's just pure oxides, but when you start looking at the splittings for other species, it kind of falls apart. And then there was someone else that wrote a paper after that kind of looked at those sorts of things and say it doesn't really work well for uh, a lot of things. So the other problem with the FE3P peak is that it's weak and there's overlaps and things like that. So unless you have a lot of iron in your system, um, it's less useful than using the 2p peak, which is the much stronger peak in the analysis. When analyzing a titanium sample containing both titanium metal and oxidized state, is it more appropriate to use asymmetric peak shapes for the metallic states and GL function for the oxides? Yes, absolutely. Uh, that's exactly what we do. We use an asymmetric peak shape for the metal and a Gaussian-Reinschen peak shapes for the oxides. It For something like a nitride or a carbide, they will also have their own peak shapes, and those things have to be taken into account. So, and we base that again on on standard samples and those sorts of things. The nitrides, I think, have some other structure going on. It's either shakeups or there's bulk plasma. There's a bunch of other stuff going on. And I have that some of that on the website, so it's that can direct you to some good papers for titanium nitride that will have different. The carbide I think looks very similar to the metallic peak with an asymmetric peak shape. So good question. Okay. How would you characterize where there is a known material where the chemistry has not been characterized on XPS and no database to compare? Uh, take your own standards, right? Like that's what we do a lot here. If we don't trust what's in the literature, or if we don't know what it is, but we have an idea, okay, we want to know, compare a system to some unknowns, we'll find some standards, make sure they're what they say they are. We'll do XRD, we'll do Raman, we'll do other analyses to make sure that they are what they are. And then we'll take an analysis by XPS. The one thing you need to watch for is that sometimes your bulk standards are not the same as what you're seeing on the surface. And this is some problems we've seen in the database as well. One example would be the PHI handbook, which shows a nice spectrum of what they say is, and I want to make sure I get this right. Actually have that here. If I look up cobalt in the PHI handbook, they have a nice spectrum of what they say is cobalt in cobalt 2 oxide, and they show a spectrum of cobalt 304. Because the surface, their bulk was cobalt oxide, but the surface was not, and we shown that through work that we've done, and you had to do kind of very carefully controlled analyses. So that's a thing that can happen is what you see from bulk analysis by XRD or by other techniques will not be what you have at the surface. So you have to think about those things about what's going on those surfaces. How accurately do we need to have the peak fitting required for publication, and what has to be shown, for example, noise and chi-square? That's a good question. Different journals require different things. The more you can show, the better. The more information you can give, the better. It, you know, it's not like we're have a page limits anymore. With supplementary data, you can put in all the information that should be there, so that if I want to duplicate what you've done, I can go and find the exact same instrument with the exact same parameters, with the exact same setup, with the exact same base pressure. I can curve fit exactly how you did it. You know, the more information you give, the better. So if you want to show, you know, how much noise is left over and the chi-square, that's, you know, I support that. Like, put as much information in as possible. Like, there's no reason not to show those sorts of things. And the problem is a lot of people do not show all that stuff, and it's almost impossible. And people wonder, well, why do we have, you know, when we talk about things like a reproducibility crisis, why do we have that? Well, if I can't duplicate what you did because you don't tell me what you did, how am I supposed to duplicate that? How am I supposed to reproduce what you've done? And how am I supposed to believe what you've done? So more is better, in my opinion. How would you peak fit if you have overlapping peaks, for example, selenium and lithium? Um, there's some different strategies. It depends on what you're trying to do. You can do, if it's overlaps in your survey spectrum and you're trying to quantify different things, you can actually do, you know, kind of curve fitting under those peaks to separate those things out. If you have overlaps within your high resolution spectra, you just have to curve fit those things in. If you have, you know, lithium and you know where that peak is, and you can be consistent about how you do it. You have to watch things like if you're trying to understand the quantification, you want to make sure you're using the correct relative sensitivity factors for the whatever components there are. An example that I've have on the website is selenium and sulfur that overlaps quite a bit, and, you know, some strategies of how you go about curve fitting, how you constrain things. We use some reference spectra of just pure selenium and pure sulfur to try and understand how to curve fit those sorts of things. All right, yeah, we've talked about charge correction already. For estimating oxide subsurface in case of mixed environment, how accurate such calculations are. Also, in the case of near ambient pressure XPS, what are the additional precautions that we need to pay attention to estimate native oxide layers and calculating atomic concentrations? Uh, Calculations are relative. They're not bad. how accurate, is it to the 0.1 nanometer? Probably not, but to the nearest, half nanometer or nanometer, depending on your calculations, it's probably in that range. Using near ambient pressure, what are the additional precautions that you need? I don't know if I can answer that. I don't have a lot of experience in near ambient pressure XPS. When it comes to being able to calculate these sort of things. So that's not something I can answer really, unfortunately. Let's see. I've read your articles, especially in applied surface science, but all papers are generally referred to the oxide base. How can I analyze metal sulfide-based species? For an example, nickel sulfide sample, how can I deconvolute the spectrum? Again, basically take standards. For the nickel sulfide, we actually have done that. We have other papers available. I think that we've done some of that work, and there's been others that have done work looking at things like nickel sulfide, particularly out of this university here. Mike Bancroft would be one. Wayne Nesbitt would be another one that has published in this area. But, take your own standard samples, standard analyses, and make your own peak shapes so that you can model your systems. That's the best way, because then now you're taking stuff that's relevant to you. It's taken on the same instrument under the same spectral resolution conditions, using your software. So that's kind of the best way to do it, is to take your own standards, but you got to make sure that you get them right and that they're clean. Or sometimes for things like something like nickel sulfide or whatever, you may have to be breaking these samples like a fracture sample so that you have a pristine surface. And if you have an attached glove box on your system, or we used to do a lot of work where we actually broke materials in situ in the vacuum of a system so that we could look at pristine surfaces. Using something, if you have access to a gas cluster ion source, that's a great way to be able to look at surfaces without reducing that surface, using where, as opposed to a monoatomic argon ion beam. Just looking through the questions here, see what else. If the defective oxide peak is too wide, how do you know what figure to constrain the full width half max to? Good question. It will depend a little bit on your spectrometer, but for the most part, a maximum of about 2 eV is kind of where that limit is. We base that on analysis. We've done a lot of different samples. I do show on the website kind of all those those other peaks that are present for a lot of the transition metals, and they're all kind of that 1.5 to 2 eV maximum type thickness, as opposed to the lattice oxide, which is generally a thinner, 0.7 to 1.2, 1.3 eV, something like that. Can you please comment on overlapping of Auger peaks of nickel and iron with each other's 2p3 spectra in the NiFe203 spectra? How do you quantify properly in such case of overlaps? On the nickel side of things, it was probably pretty good. The nickel peak was, I don't think we saw too much overlap. I know in the iron peak, the overlap of the nickel Auger is a little more problematic. The papers from, again, from Tony Hughes and Chris Easton recently also discuss how to deal with that. And basically, it's a matter of you can model in what that Auger peak contribution should look like underneath that iron 2p peak. And so it can be a problem. You've got peak overlaps. The easy way to deal with that is if you have a different X-ray source that you can then use. So if you use magnesium or silver, you're moving those Auger peaks out of the way, and then the peak shapes that you get will be the peak shapes that you get. So that's a possibility if you can understand that you're going deeper into the material, and that might change things as you go deeper. But that's the easiest way, is to actually use a different X-ray source to move those Auger peaks, if it's available. Sometimes, or you need to find someone that can do that sort of thing for you. I went through a paper in which the author fitted the curve with Ni203 and used some fitting software, a analyzer. They suggest it is not NiO, that it is Ni203 if you oxidize below. Again, this is something that we've seen where if the shape looks like NiO, it's probably NiO and not this, this Ni203, which is not a well characterized. It's not a well characterized nickel 3 oxide. So yeah, take it with a grain of salt, and compare to these standard spectra. Probably not correct, but I don't know. I haven't seen the paper. We know that the difference between the two p3 halves and two p1/2 spin orbitals should be around 5.7. And I take it this is for titanium. However, I found some papers with over 6 eV sometimes, and even the Photoelectron max would not be the same. So how is this deviation special for the case of TI2? That's actually true. And so the spin orbit splitting can change between different species. So the metal spin orbit splitting is a little bit different from the oxide spin orbit splitting. And again, you would only know that if you actually took standard spectra. Generally for species that are oxidized, the spin orbit splitting is going to be relatively similar. So the 5.7 or whatever it is for the TiO4 will be thing, but the metal may be different. And then the position or the area, the full with half max changes. Yes. So what's happening with titanium between the 2p3 half peak and the 2p1/2 peaks is a phenomenon called Koenig-Kroster, I can't even remember. Koster-Kronig broadening of the 1/2 peak. And I won't explain it because I don't remember exactly what the process is, but there's a physics process, whereas that 1/2 peak is very much broadened compared to the 3/2 peak. And that's going on for titanium. I think it goes on a little bit for scandium and a few other things, but that's why you're seeing a change in that. And so there's weird physics that's going on that's causing these things. It's just something you have to be aware of. If you're working with titanium, that's something you're going to have to be aware of for that. And we do talk about those sorts of things in the papers that we've published. There is a peak in my carbon high resolution spectrum in the binding energy of lower than carbon-carbon, lower than 283 EV. What can be related to? That's typically a carbide. And so if you have a metal, you can have these carbide formations. They are going to be at that position around 283, 283.5, somewhere in that range. So that's a carbide. It's not an organic peak. Easy question. I'm not familiar with CAS XPS. What to use for fitting asymmetric metallic core levels? It's not a combination of Gaussian Lorentzian. Different software is going to have different functions to fit this asymmetric peak. We use CAS XPS. There are other ones that are available. There's different ways of calculating and modeling that asymmetry. Some of them are better than others. An older model would actually model the area under peak, but it would carry on up, and so you get an over-exaggeration of the area under the peak. And so then they use these truncated models, which would stop after a certain binding energy, and then there's these new models that more accurately fit this area under the peak. So it's really just a math game, and it depends on who the developer is. And so sometimes I get the comment, well, you're giving this how you fit this asymmetric peak shape for CAS XPS, but not everyone uses CAS XPS. I get that. What you kind of have to do if you're using other software or other things and you're working on, say, okay, you're constantly working on nickel or you're constantly working on iron, and you need to know that you're going to have to take an analysis of an iron peak or get a spectrum and figure out what that asymmetry looks like in your software and try to understand, is it modeling this correctly? How do they model it? And it's kind of a question. It's you almost have to kind of talk to them. And in order to get it right for us, I actually, talked to the developer of the software to see what math they were using. I had to dive into that kind of depth level to get the right amount because I needed to know how the actual area under these curves to do these calculations for metal for oxide thickness correctly. If you're giving too big of an amount for the metal peak, then you're throwing off your calculations. And so yeah, these are kind of nuances and things that are. This is why XPS is. There's a lot of things that are not easy with XPS compared to a lot of other spectra. People look at XPS and go, oh, it's easy point and shoot type of stuff. You can just take a binding energy and an area under the curve, and it's easy. Kind of like like EDX, right? Where that is the case, but it's not the case for XPS. XPS has a lot of nuances that can really throw wrenches into how you're looking at these sorts of things. They also ask, can you use a combination of Gaussian Lorentzians to model that asymmetric peak shape? Yes, that will work. All you're doing is trying to get an area under the curve. And so however you do to get that area under the curve effectively, but it has to be based on, your standard spectra. But yes, that is certainly, if that works to get your area under the curve and you're happy with that is giving you the right amount, then that certainly does work. Regarding the Shirley background in the nickel 2p 2/2 slide, why is there an offset applied? So this is again, if you look back here on this nickel slide, if I don't have an offset, this dotted line here, will it gives you the seeing that it will cut through and you'll lose some of this area under here if you don't use an offset. And this offset amount changes depending on how much this background goes up or down. This is a problem where the math for the Shirley background calculation can't handle all that's going on here. And so it's one of those areas where the Shirley background isn't great, isn't perfect. So you have to do some modifications in order to make the curve fitting work correctly. But yeah, I talk about this in the paper and how to make this work. So it's like an iterative process to make this work. It does work though. It does work pretty reasonably once you do that way. What are the best ways to determine correct RSFs, and when is it fair to use the CASA default ones? If you don't have any other choice, the CASA default ones will work and will give you reasonable results. If you can get the correct relative sensitivity factors that match your instrument, that's probably more appropriate, and you can do that. For example, we have Kratos instruments here, and we're able to get the correct relative sensitivity factor table and use that in CASA XPS instead of the standard ones. That being said, a Schofield table of RSFs works pretty reasonable. As long as you're not jumping between different RSF tables while you're trying to compare materials, that would be a problem. But if you're using the same stuff over and over again, sometimes some of those RSFs we know that aren't working right. An example would be we've developed our own relative sensitivity factor for using the magnesium Auger line as opposed to the magnesium 2P or 2S line. The one that was given for Kratos was just, it gave nonsense numbers. So we developed a number that we can use that works. Some things aren't available. We do a lot of work with nuclear materials, so things like thorium and uranium. Some tables we don't have access to that, so we've developed our own relative sensitivity factors based on standard samples to use in those cases. I have both a monatomic and cluster ion source. How do I determine which is appropriate for specific samples or for specific processes, etching, cleaning versus depth profiling? So a monatomic source is great for drilling into materials very quickly. But you're not worried about whether chemistry is going to change or whether oxides are going to reduce or materials are going to reduce. A cluster ion source, depending on how you tune it, is very good at depth profiling into materials while maintaining the chemistry of those materials. and it will depend on the manufacturer. So I know Kratos gives us a list to say, okay, these settings are really good for looking at organic materials and depth profiling through organic materials. These settings are very good for just surface cleaning, like removing adventitious carbon and those sorts of contaminants. These settings are good for depth profiling at a reasonable speed through metal oxides while maintaining chemistry. And so it depends on your manufacturer, but they would have recommended settings for doing these different types of things that you want to do with the gas cluster ion source. I have to say, the gas cluster ion source is a game changer for analyzing materials. We rarely use a monoatomic source anymore for any of our work. All right, so how can we do peak fitting in the range of 850 to 870, but do the offset and binding energy of 860, 886 EV and nickel 2p3 halves? So yeah, I've got a background that goes across the entire 2p3 half spectrum, but I'm only fitting the 3 halves. Uh, the background goes across the entire 2p spectrum, but I'm only fitting the 3 halves peak. And the way that works is that everything is well constrained. If you just had peaks under there and told it to fit, you'd fit a bunch of peaks under the 1/2 peak, and it wouldn't work. So all the peaks under that main peak, the 3/8 peaks, are so well constrained that they can't move around or anything like that. So that's how we make that work. Okay, instead of using a background offset, would it also be correct to use 2 Shirley backgrounds, one for the 3/2 region and one for the 1/2 region? Yes and no. It can work that way. The problem is with nickel is the 2p uh, the 2p 1/2 peaks of the metal overlaps with the shake-up structure of the 2p 3/2 oxides spectrum. And so that kind of inflection point here isn't necessarily where the baseline is. That there can be other stuff in there, and so you'd never quite get your baseline where it needs to be by using 2 baselines. That's why we use the offset. For the carbide and the binding energy that you see in the carbon peak, if you see a carbide in the carbon peak, should we also see a carbide for like a nickel carbide if you're looking at nickel and the nickel 2p as well? Yes, you should. The problem is a lot of times the carbide peak is almost at the exact same binding energy position as the metal peak in the nickel or other species as well. Like titanium is similar where the titanium metal and titanium carbide overlap. And so it becomes very difficult to elucidate which one's which. You can do kind of calculations relating how big your carbide peak is in your carbon 1s peak to how much carbon you have in your survey spectrum. Then go back and say, okay, well, if I have that much carbide, how big should that peak be in the nickel 2p spectrum? So you can do those sort of calculations. And then you can go, okay, well, I know that I should have a peak of this size for carbide in the nickel, then the remainder would be metal. So you can do those sort of calculations based on the information from different peaks. I've seen the degree of asymmetry depends a lot on the specifics of the metal species, nanoparticles, clusters, surfaces coordinated or not to ligands. Is there a way to predict the exact degree of asymmetry that can change a lot of the quantification of the different species? That I don't know. I've seen times when you think there should be an asymmetry and there's not an asymmetry, and vice versa. Um, yeah, I don't know the answer to that, and that will because nanoparticles can behave differently, and as you add stuff, it goes from, even though it's maybe zero valent material that should be, it's no longer conductive, and so the asymmetry will go away because it's not conductive anymore. But yeah, that's a very specific question. I'd have to see the more nitty-gritty of that to make that work. XPS mapping. As we go smaller spot size, the data peak distortion increases. Do you have any recommendation to collect good data for mapping for a spot size of 10 to 20 microns? That can be instrumental in nature. And so there's two types of instruments. There's a microscope type analysis and a microprobe type analysis. So the Kratos and the thermal instruments, when they do imaging, they're doing a microscope type analysis. And so you take an image that the X-rays are kind of a flood across the surface, and you're taking an image from a certain area. To do a small spot analysis, your X-rays are very weak across that small area, and so it takes a long time. If you go to the Phi instrument, that's a microprobe type analysis. And so to do small spot analysis, they focus the X-rays down into a smaller and smaller spot. And so you're still getting a lot of photoelectron flux from that smaller spot. And so it's much better at taking that small spot analysis. You'll get much stronger signals. So it's just a different configuration of the instruments. I know the newer Kratos instruments are now coming out with a source that can do both. So in standard mode, it'll be a microscope type mode. But if you want to do small spot analysis, you can actually focus down that source size to take a small spot analysis. So it's instrument specific as to why that's an issue. And it just, if it comes down to when whoever's purchasing the instrument, if they make those decisions based on, okay, I do a lot of small spot analysis, I will take one instrument over the other. So they have pros and cons on how they're set up. All right. Based on the condition of the experiment, there is no possibility of having nickel carbide, but I see that a carbide peak is in my carbon spectrum. How can we justify that? I don't know. Do you have other metals in the material? But if your carbon 1s says there's a carbide, there's probably a carbide. So I don't. And you say your experimental conditions say that that's not possible. I don't know the answer to that. You'd have to look at your experiment and try to justify as to why there isn't a carbide. But there's not much else down at that carbon 1s peak. And if your samples are, well, they're not differential charging, if you can rule out differential charging, so you're doing your analysis and you change flood gun settings and things like that, and the peaks don't move around, everything stays stable, then if it's a carbide, it's a carbide. But you'd have to rule out those other things. Yeah, and here's a final comment, and I think we're going to look to wrap things up very shortly here. I think in general, we should all explain in way more detail the logic behind our fittings and our papers, no matter the length. I totally agree. The more information you can give about these sorts of things, the better it is. All right, I think that's enough.
Yeah, you did a great job. That's answering all those, I don't know, hundreds of questions in 3 hours. Okay.
But it's a lot of the questions I've had a lot of those questions before when I go do workshops and stuff like that in other places. Everyone's struggling with the same sort of thing, and that's why like the website. That's why we kind of got started doing that website. Is like we're hearing the same questions from students and researchers over and over again. So we're trying to answer those questions and have a place where people can get those answers.
Yeah, so in case someone wonders, we have 2 recordings. We will merge them and we will email them to all registrants. We also will put them on our CORRECT homepage. So if you maybe Nuggets, can you put it in the chat, like the homepage, in case someone didn't sign up or doesn't get the email? We just give you the homepage where to look for. We will also post it on LinkedIn so you can find it.
Perfect.
So thank you, everyone.